In 6.3, we will talk about the two laws of thermodynamics. Thermodynamics is defined as the study of energy and the energy transfer between physical matters. Um, Before understanding thermodynamics, we have to talk about what the system and their surrounding is. The system is the matters in its physical in its environment that are relevant to a particular case for energy transfer. So, for example, when we talked about heating a pot of waters, the system is going to be the stove, the pot, the water, anything within that that are immediately relevant to that pot of the heating a pot of that water. And we will have to, anything that else that are outside the system or basically outside of that pot of water, we will consider that a surrounding. So for the surroundings, for our example, it will be the air surrounding it, it will be the buildings, be everywhere else, just except what we're really focusing on. So our system is just basically a focal point, and everything else that is not really included in the system will be considered the surrounding. There's two types of system. There's an open system and there's a closed system. So in an open system, there will be energy transfer between the system. So the example that we just talked about, it is a open system because you have an energy transfer within the system, between the stove, the water, and the pot. And we also have energy transfer within the surrounding because you're losing heat into the surrounding airs, thus it is an open system. And we can also have a system as a closed system where there's no energy transfer at all, that it is a closed self-sufficient system, and usually this is not really what you observe in nature or in your body because biological organisms are mostly open systems, and there will be energy exchange between them and their surrounding. We use our chemical processes to heat up our body, and we also losing our heat to the environment. We also consume energy, and it will also release energy as well when we're doing a certain amount of work. Having this understanding, now we can talk about the first law of thermodynamics. So the first law of thermodynamics states that the total amount of energy in the universe is constants. And the derivative of what that statement is that there will always be the exact same amount of energy in the universe, and the energy can only be transferred from one place to the next. It can transform into different forms. For example, like light energy, there's chemical energy, all the energy that we talked about in previous sections, but the energy cannot be created or destroyed. So in our example, we see a light bulb, you see electrical energy being transformed into light energy. In the gas stove example that we just talked about, in the octane gas, we have chemical energy that's stored within the chemical bonds will be transformed into the heat energy. With plants, we take sunlight energy from the sun and we transform that into chemical energy being stored in organic molecules. And this process is the last one that we talked about is photosynthesis. Photosynthesis is the most biologically useful energy transformation on Earth because that's how we obtain energy from the sun, and that's our energy input. Without photosynthesis, we won't be able to have energy to form more complex molecules. Then we have our second law of thermodynamics that has to do with the disorder, or if you remember, that's the entropy, the delta S that we see from 6.2. Now, it states that every energy transfer or transformations will increase the universe entropy or will cause more disorder. If you think about this, this makes sense. As you do any kind of work, you do homework, you listen to this lecture, you're sitting there, and or even the biological process within your body, when they're occurring, they actually produce heat as a byproduct, and not every system is efficient, so we will basically lose heat for everything that we do, so that will contribute to the overall universe entropy, and it will always increase. And because of that insufficiency of the processes. So those heat lost to the environment, those are unusable energies, so we are not considered that as gift-free energy, it is just heat as a byproduct. So that's how we define heat. Heat is the energy that transfers from one system to the next that is not doing work. We talked about heat loss in the biological processes. But that heat is also used to maintain your body temperature as well. So there's also some useful application of that lost heat as a unusable product. And in a physical world, when we see a flying airplane, that airplane has to use burnt gas. The gas has to be burnt up, and in that process, you're also releasing heat to the surrounding air as well. And there's also the frictions with the surrounding air that cause heat loss as well. And this heat will actually be used to heat up the air molecule surrounding the airplane. Similarly, how that lost heat is used to maintain our body temperatures. So the second law of thermodynamics has to do with entropy. The entropy, as we talked about before in 6.2, now we will really defining it. It is a measure of randomness or the disorder within a system. So when we have a high measure of entropy, there will be a lot of disorder and we don't have a lot of energy. When we have a low energy within a system, then we don't have a lot of disorders. Everything is very orderly. It formed complex molecules and it has a lot of energy. So when a chemical reaction reaches a state of equilibrium, it will be more disorder, so our entropy will increase. Diffusions from a higher concentration to a lower concentrations will go to an equilibrium state, and that will cause our entropy to increase as well. So as you can see here, within a solid forms, there's more order within a system. Within a liquid form, there's more order. So to go from a solid state to a liquid state, we're actually increasing our entropy. And for living things, we're actually really highly ordered because we constantly have energy input to maintain that orderness. And that state of orderly, we call it the state of low entropy. So if we have high entropy, all of our cells will be everywhere. We won't be together as one individual mass, and it would not be good. So as we mentioned before, this is the reiterations of the second law of thermodynamics, stating that the total universe entropy will constantly increasing, and that is because of the inefficiency in processes where you will have heat loss no matter what you're doing. And to sum it up, living things are basically in a continuous uphill battle against this constant increase in the universe entropy. So we're trying to constantly fighting against that disorder and trying to create order out of the chaos. We're forming complex molecules, we're making polymers, we're making proteins, we're making lipids, membranes, and have cells, and that requires a lot of energy. That's why we have to eat every day. That concludes our 6.3.